Now we can see different terms relating rotational motion. First one, angular velocity. It is represented by omega. Consider a rigid body which is rotating about a given axis. So here it is the axis, the object is rotating about the given axis in this direction. Okay. Now, P is a particle when the object rotates, when a rigid body rotates about the given axis, each particle on the body, it is also moving in a circular path, that you know. Okay, it is moving in a circular path in a plane perpendicular to the axis. So here P is a particle, it is also moving in a circular path with velocity v. And when it moves in a circular path, it subtends an angle delta theta at the axis. Okay, when the object moves in a circular path, let between the 2 points P and P dash, it subtends an angle delta theta. Here, this is the radius. Now, angular velocity is given by angular displacement divided by time. So, it subtends an angle delta theta or d theta. So, angular velocity is given by angular displacement. Here, what is the angle? Delta theta divided by corresponding time, let it be delta t. So, angular velocity is given by angular displacement by time, that is delta theta by delta t or d theta by dt. And its SI unit is angle by time, no? Angle SI unit radians, so radians per second. So, this is called angular velocity. Now, what is the relation between linear velocity and angular velocity? In the circular motion chapter, we have studied the relation between linear velocity and angular velocity is V is equal to R omega. So, in vector form, we can write vector V equal to omega cross R, where omega is the angular velocity, R is the radius or distance between the point from the origin. Okay, so in vector form, the relation between linear velocity and angular velocity is V equal to vector V equal to omega cross R, where omega is the angular velocity and R is the radius vector. Now, second term in rotational motion is angular acceleration, which is represented by alpha. Angular acceleration, we know acceleration is the rate of change of velocity. Similarly, angular acceleration is rate of change of angular velocity. Okay, so angular acceleration alpha is equal to d omega by dt. Rate of change of angular velocity is omega, therefore d omega by dt, and its SI unit is omega SI unit radians per second. So here SI unit is radians per second square. It can also be written as d by dt of omega. What is omega? D theta by dt. So it can also be written as angular acceleration alpha equals d square theta divided by dt square. In vector chapter, we have studied acceleration. The linear acceleration is d square x by dt square. Okay, d square displacement divided by dt square. Similarly, angular acceleration alpha can be written as d square theta divided by dt square. We can do a question. Find the linear velocity of the particle in a rigid body moving with angular velocity omega and having position vector r. Okay, so omega is given as 3i minus 4j plus 5k and vector r is equal to minus 2i plus j minus 3k. We have to find out the linear velocity. We have the linear velocity v equal to omega cross r. V equal to omega cross r. So we have to find out the cross product, isn't it? So how will you find out the cross product? This is the method. By using the determinant method, we can find out the cross product. Omega, here first we have to put ijk. That's the method, no? Omega, omega here 3, here minus 4, here plus 5. Then second vector is r. So here minus 2, here 1, here minus 3. This is the method. Already we have studied in vector chapter, isn't it? So we can write, how will you find out the cross product? I into, leave that row and column. Here 4 into 3, 4 3s are 12. Here minus 12, minus 5. Then second term is negative, minus j into, leave that row and column. Here minus 9, minus 10. This is negative, no? So plus 10. Then second last term is k, positive, plus k into, leave the row and column, 3 minus 8. Okay. And after simplification, 7i minus j minus 5k. So that is a velocity vector. Okay, so if omega, angular velocity, and the position vector are given, directly using the cross product omega cross r, we can find out the linear velocity. Then the third term we have to study is torque, otherwise called moment of force. We know that in the motion of a rigid body, it is a combination of rotational motion and translatory motion. For example, the motion of the bicycle, the wheel of the bicycle. When the bicycle moves in the forward direction, so wheel exhibit, okay, a wheel of the bicycle exhibit rotatory motion, and it is also moving in the forward direction, and it exhibits translatory motion also. Okay, so motion of the wheel is the best example for translatory motion and rotational motion. For another example, if the fan is rotating about the given axis, it has only rotatory motion. There is no translate, the object is not moving from one point to another. So it has a translatory motion. With the axis fixed, it moves. Then if the motion is of a spinning top, so there also the point of contact remains constant, but the axis of rotation slightly gets tilted. So it forms a cone. Clear? So these are all examples for rotatory motion. In some cases, it is a combination of rotatory and translatory motion. Example, the motion of the bicycle. We know a door is a rigid body which can rotate about a fixed vertical plane or vertical axis passing through the hinge. Like this is the door and this is the hinge. It is fixed at the hinge, and when the door moves or when the door is opened and closed, we have to apply an external force. Clear? So here the axis passes through the hinge. The axis of rotation passes through the hinge. So when door is a rigid body which can rotate about a fixed axis passing through the hinge, and what makes the door rotate? We can, it is clear that we have to apply an external force, then only the door moves. So unless an external force is applied, the door does not move. And whereas the force of given magnitude and should be applied at right angle to the door. So in order to open the door, we have to apply a force in the right angle direction, then only the door moves. Okay, if a force is applied here, the object does not move. At the hinge, we have to apply a force at this direction, then only the door moves. Clear? So the importance of torque is we have to apply force in order to rotate the object and in order to move the object, and at what position we have to apply the force. So both are important. We have to apply the force in order to rotate an object, and the position also is very important. If the force is applied at the hinge, the door does not move. We have to apply a small force here at the other end of the hinge, then only, or the one side of the door, then only the door moves. So in order to rotate or in order to move a door or in order to open a door, force is needed, and the position of force also very important. Okay, at the position at which the force is applied, that is also very, very important. So it is not the force alone, but how and where the force is applied is important in rotational motion. Okay. Now, torque is defined as the rotational analog of force. It is called a torque. Rotational analog of force is the moment of force called a torque. Moment of force or rotational analog of force is called a torque. Okay, so that is the corresponding in linear motion, it is called force, and the corresponding force in rotational motion is called a torque. So that is the rotational analog of force. We can consider a rigid body rotating about a given axis. P be a particle on the rigid body which is at a distance r from the origin. Let this is the origin, or r from the axis. Okay, O be the origin and r be the position vector of the particle. If a force F is acting on the particle, this is the direction of force. Then torque is defined as, we know torque is defined as moment of force. That means torque is equal to force into, this is the general formula, force into perpendicular distance of force from the origin. This is the general formula for torque. Force into perpendicular distance of force from the origin. So here force is F into what is the perpendicular distance of force from the origin, that is not r. R is not perpendicular. So how will you find out the perpendicular distance? This is the perpendicular distance. We can extend the direction of force, and this represents the perpendicular distance. Is it clear, children? So torque is defined as force into perpendicular distance of force from the origin. So force is F, no problem. Perpendicular distance of force from the origin. Perpendicular distance of force or direction of force from the origin means this is the perpendicular distance. How will you find out this distance? Clear? For that, let theta be the angle between F and R. Distance between the point and the origin, that is R. So theta be the angle between F and R. So since this is theta, this is also theta. Then how will you find out the perpendicular distance? Using which trigonometric function we can find out the perpendicular distance? We can take sin theta, isn't it? Sin theta is equal to opposite side, that is the perpendicular distance divided by hypotenuse. Hypotenuse is R. This distance is R. So perpendicular distance is given by R sin theta. Clear? So perpendicular distance is given by R sin theta. So torque is force into perpendicular distance of direction of force from the origin. So perpendicular distance of direction of force from the origin is this distance. This distance is actually R sin theta. So we can write torque tau equal to R F sin theta. So we know AB sin theta. What is this AB sin theta? We know it is A cross B, isn't it? A cross B. Similarly, R of sin theta is actually vector R cross vector F. So torque is given by the formula tau equal to R cross F. So torque is the rotation analog of force and it is given by R cross F, where F is the force acting on the object, R represent the position vector from the origin, the point P. So that distance is called the R. Clear? So torque is defined as force into the perpendicular distance of force from the origin, that is actually R sin theta. Hence torque tau equal to R cross F. R is the distance, F represents the force acting on the particle. Clear? Here torque is represented by a Greek letter tau. Okay, so this is the Greek symbol tau. So torque is given by the formula R cross F and torque is represented by a Greek letter tau. This is pronounced as tau. Okay, children. So torque is the rotation analog of force. It is moment of force. Moment of force means force into perpendicular distance. So anything into perpendicular distance is called moment. So torque is defined as moment of force, or it is a rotation analog of force, and it is given by tau equals R cross F. Now the next term is angular momentum. It is represented by L. It can be represented by small letter L also. So angular momentum is defined as the moment of momentum. It is a rotation analog of momentum. So earlier we have studied rotation analog of force is torque. Similarly, rotation analog of momentum is angular momentum, and it is also defined as moment of momentum. Consider rigid body rotating about a given axis. Here this is the axis. The object is rotating about the given axis with angular velocity omega and linear velocity v. Here P be a particle. This is a particle which is at a distance r from the origin or r from the axis. Let capital P, this P represents, vector P represents linear momentum acting on the particle. P is the linear momentum acting on the particle. So this is the assumption. Consider an object rotating about the given axis. P be the position, and the P represents, vector P represents the linear momentum acting on the particle, and it is that the particle is at a distance vector r, position vector r. Theta be the angle between vector r and vector P. Okay, r is, this is the direction of vector r, this is the direction of linear momentum, theta be the angle. Now we have angular momentum is defined as momentum into perpendicular distance. Okay, moment of momentum. Moment of momentum means momentum into perpendicular distance. Here momentum is P, perpendicular distance. How will you find out the perpendicular distance? This is the perpendicular distance. Okay, if you take sin theta is equal to perpendicular distance divided by r. Sin theta is opposite side divided by hypotenuse. Here the perpendicular distance is r divided by hypotenuse. Perpendicular distance divided by r. Okay, so sin theta is equal to perpendicular distance we have to find out divided by r. Sin theta is perpendicular distance divided by r, or we can write angular momentum is equal to PR sin theta, or angular momentum L equal to R cross P. Clear, children? So earlier we have studied torque tau equal to R cross F. Similarly, angular momentum L equal to R cross P, where R is the position vector, P is the linear momentum. Clear? So angular momentum is defined as the rotational analog of momentum, or it is defined as moment of momentum. Moment of momentum means momentum into perpendicular distance. Clear, children? So angular momentum L equal to R cross P, where theta is the angle between vector R and vector